So let's go for the next presentation. This presentation is from Salam's.
Salman.
Please pronounce that for me.
Salman. S-A-L-M-N. Salman.
Last name.
Salman Shaikh.
Yeah, thank you. I'm sorry for that. I apologize. Are you a PhD student?
Yeah.
Yeah, PhD student in KAUST. And the presentation is titled Exposing Virtual Aimbots in Game Honeypots for Proactive Cheat Detection. I'm a player, so I expect much of this presentation.
Okay, that's good. Okay, hello everyone. My name is Salman Shaikh. I come from King Abdullah University of Science and Technology from Saudi Arabia. And in this presentation, we will be talking about video games, more specifically cheating in video games, and how we can detect visual aimbots via honey tokens. So let's start off with a quick introduction to what are aimbots, which I'm pretty sure you guys are aware of. These are just software programs that enhances the performance of a cheater by automating the process of finding and shooting at the opponent. An attacker who is equipped with an aimbot significantly increases their reaction time and reaction speed, obviously compared to an honest player. This has been a problem that has been seen since the very early days of shooter games. Now, in the literature, we have identified two types of aimbots. The first one is your typical memory-based aimbots, and they work by basically attaching themselves to the game process and reading the memory for valuable data structures, typically to extract enemy positions or other kind of coordinates, and then performing some mathematical operations, vector calculation, and injecting this directly into the game. They're often paired with other types of aimbots or trigger bots to basically obtain a completely automated shooting system, where the aimbot will aim at the opponent, and the trigger bot, once this aim has been directed at the opponent, is then shooting at it. However, as I mentioned, this was a problem that was seen for a very long time. Current games are now shipped with anti-cheat systems such as Easy Anti-Cheat, Vanguard, BattleEye, and so on, and they work at the kernel level to detect such cheats, basically by looking at any processes that attempt to manipulate the game memory or read the game memory to basically change for their favor. Again, it does work somehow to a certain extent. There are still ways where cheaters kind of use different kinds of hardware, such as DMA or something, to bypass these. But this is the current commercial anti-cheat mechanism that first-person shooter or shooter games rely upon. Another type of aimbots are visual aimbots. Now, they work in a completely different way. They basically utilize pre-configured or pre-trained computer vision models that run alongside the game. And while the game is running, they analyze the live stream data as seen by you or the attacker, instead of ever accessing the game memory. And this live screen data is then seen by the model. They make the bounding boxes, and the screen coordinates are then extracted from the live screen data, and then the device level input is then injected. And this is actually being used more and more in practice, and it's not just in theory. And if you actually search up on YouTube or somewhere where you search up aimbots for Fortnite or aimbots for Valorant, you will not see your typical memory-based aimbots. You will see maybe the first two videos, I just used ChatGPT to make my aimbot, because this is becoming more and more common, and they evade the traditional commercial anti-cheat systems. And now you may consider why and how this is the case. So for example, you have two PCs. Your first PC is where you run the game, your host machine, which is running with the anti-cheat system, and all you have to do is take the HDMI out, or the video output, have it input into your second machine where your visual aimbot is running. In the same screen space, in the same resolution, where the visual aimbot makes the bounding boxes on your opponents, and then this is just then sent as a USB input injection, which your anti-cheat systems doesn't think as suspicious at all, and it works normally. So, what to do? I mean, this is something that's actually becoming more prevalent, and currently there is no solution to prevent these kind of visual aimbots. And as the technology becomes more and more faster, your computers become faster, these models become more optimized and better, this is something that needs to be tackled. This is where we propose our own method, which is called PATCH, or Proactive Adversarial Traps for Cheaters in Multiplayer Online Games. The idea here is to generate adversarial patches of different sizes, which will serve as honey tokens. Now, when we talk about patches in the context of AI or computer vision or object detection, usually they're presented on the screen so that the model kind of disrupts, classifies one class as another class, or just doesn't work at all. However, in this case, we actually want to generate patches that has intrinsic features to deliberately trigger the attacker's visual aimbot. Now, from the attacker's point of view, it's working completely fine. They have this amazing visual aimbot that detects these opponents. So they have no reason to think that it will detect something else. However, if we can develop these patches and find multiple occurrences of this behavior, we can accurately classify the presence of a visual aimbot cheater. Now, to do this, we use our own custom Unreal Engine-based open source game that we developed ourselves, which has the capabilities of logging different fields, automating actions so that we can repeat our experiments, and ultimately allows us to act as both from the attacker's point of view and also from the defender's point of view. Now, from the attacker's point of view, they just want a generic working visual aimbot for their game. To do this, we utilize a pre-trained YOLO 11 medium-sized model that's provided by Alterytics. And the reason we use this, as opposed to any other object detector, is because it's the most commonly used model in practice because of its balance between accuracy and its latency. And we will show you an example of an open source model for a commercial game that also uses YOLO as well. And then all we do is really just fine-tune it to detect one class, so in this case, the opponent class or the player. And then we have and then we train the model on diverse images and just have a simple test that we typically do in computer vision or object detection tasks. And from the results, we see that it seems like we have a working visual aimbot, right? But just to make sure that everything is still well in place, we run the game, we run the visual aimbot alongside it, and we see that it can make bounding boxes with rather high confidence scores. Okay, now the attacker is quite happy. Now let's pivot to the defender's point of view. So our approach is actually a white box approach, where the defender can leverage the cheater's model to generate honey tokens designed to trigger it. Now you may consider, okay, this is cheating, right? Why are you assuming a white box approach? Why would you be able to have the cheater's model? Actually, this replicates the real-world scenario. You have to differentiate between a cheater and a cheat developer. Cheaters basically download these models, these weights, and everything from open sources, Discord channels, Reddit, other websites. So the same model that they download, the defenders or the game developers also have access to it as well. So this white box approach is actually the real-world applicability. Of course, it's possible that the cheater is using some model that the defender or the game developer has no idea about. In this case, they will have to rely on a known surrogate model to develop the patches and hope that the transferability between those models occur. We can talk about this offline. We have done those tests, but the black box approach is not part of this presentation. So how do we generate the patches? Actually, it's rather simple. We start by initializing the patch on top of the gameplay images, and each patch is initialized with values randomly drawn between 0.25 or 0.75 independently for each pixel across all 3 RGB channels. Next, we generate the patches. This involves passing the patched image through a frozen detector, calculating the gradients, and updating the pixels by performing gradient ascent. This process is done iteratively. And then we have to select the patch. We select the patch based on the best patch state that was observed during this patch generation, and we see if it can trigger the model with at least 75% confidence. If it doesn't, okay, let's restart again. If it does, we accept that patch. And then we check if, for a particular size, which we'll see in a couple of slides, if we have developed at least 100 patches for those. If yes, then we stop this process, and if no, then we keep on continuing. And this is an example of a patch size for different sizes. So for each patch size, we actually developed 100 patches. Okay, again, in theory, it looks like it does work, but just to make sure everything is working fine, and we perform a sanity check, and then all we do is we render this patch from within the game itself and run the visual aimbot from the attacker's point of view. And even in this, the patch size of just 10 by 10 actually triggers the model with 80% confidence, where the model thinks that this is actually a player. Okay, so now we have seen the attacker's perspective where the visual aimbot is working. From the defender's point of view, we see that the patches are working. So how do we evaluate this? So all of these patches are rendered from within the game as 2D textures so that they actually retain their pixel values that were optimized during the training procedure. and they're only rendered in the game for just 0.1 seconds or 100 milliseconds. So like I said earlier, we developed 100 patches for all of these patches. So all we do is randomly for different patch size, we show them on the screen while the game is running, while the visual aimbot is running, and then we compare them. So since we can act as both the adversary, as the attacker, and the defender, we utilize a dual logging system. Whenever the patch is deployed from within the game, we calculate its absolute coordinates, what is represented on the screen. And then from the visual aimbot, which makes a bounding box and the associated class scores, but we're not really interested in class scores because there's only one class, all we have to do is compare these two logs. And then we can see whether or not this patch actually triggers the visual aimbot, and also look at its localization as well. All patch analysis experiments were conducted for many trials across different runs, across different settings, and we report the average of it. Okay, now from this result, we see that if we have a patch size of 15 by 15 at least, we get pretty good score, an F1 score of 93.4% and a true positive rate of almost 88%, right? So it looks like the threshold should be 15 by 15 for a visual aimbot to be triggered by our patches. But this is where we should not be confused from these results. Even though the 10 by 10 patch shows an F1 of 57.1 or the true positive rate of 40%, this doesn't mean that it doesn't work, right? All we have to do is we have to show more of it. And the more of it we show, and then we just have to correlate how many times whenever we show this 10x10 patch triggered the visual aimbot as well. Again, all of this was actually done on our test bed using Unreal Engine-based game. However, we wanted to see if we can actually work for a real game as well. So what did we do? We used Fortnite as an example. We run Fortnite, and we obtain a visual aimbot online, free to use, which also was YOLO 12, I think. And we download the model, and we train the patches the same way we train for our custom game. And we develop the patches. And then we run, and then we show the patch superimposed on top of the game. So obviously, we don't have access to Fortnite's game environment, so we just superimposed it. But it's the same thing as doing it from within the game, or we're superimposing it. And then we run it at two different levels. When we run it at a confidence of 50%, we see that the visual aimbot that we downloaded online makes a green bounding box on the opponent and on the patch as well. However, when we increase this to 75%, the visual aimbot actually stops making a bounding box on the actual opponent, but continues to make a bounding box on the patch. So this shows that we can actually trigger or make patches that the visual aimbot classifies more as an actual player than the actual player itself. Okay, this was basically what we have done in a very brief and concise manner. I think we're the first ones that have used the concept of patches as honey tokens rather than disrupting the model. We see that it is indeed effective for all patch sizes. Of course, there are some limitations. We see that the higher the patch size is, the better it is in terms of results. There's obviously we're only looking at one model, so there are some issues in cross-model transferability, but we can talk more about this offline since we did do some experiments for this as well. And some future work, there's a lot of future work that we can do on this. The first one that we thought of is instead of using a random initialization of the patch, having some kind of base based on the characters or based on the scenes within the game, so that it already has a good starting point and develops better features, triggering the model in a much more better way while remaining stealthy as well. And obviously, there's some mitigation techniques that needs to be combined with it. For example, like I mentioned, the concept of trigger bots. If we present this patch and then the attackers aim shifts at it and shoots at it, okay, the server getting some information because it shot at it. However, let's say they don't use a trigger bot. All they're using is an aimbot. So it will move to the patch, but that's it. So the server actually, or the game developer, gets no information from it. In this case, what we can do is we can basically flood their viewport with patches, so it keeps on moving their cursor, making the game basically unplayable for them, forcing them to turn off their aimbot. Again, there's many stuff that we can combine it with and a lot of potential future work, which is something that we are working on currently. So that's it. Again, if you're interested in talking about video games, cheating, different types of cheat, more network level, anything, please feel free to reach out. And we're always looking for players to play our games to gather a more enriched data set. So yeah, that's it. Thank you.
Thank you. We have time for one or two questions.
Yeah, one or two questions.
Hi, thanks for the talk. In the cheating model you presented at the start of your talk, from what I understood, the second PC injects like USB to the first PC to move the mouse, right?
Yeah.
Have you ever tried to analyze the movements of the mouse to consider if it's human movements of a mouse or generated by a PC?
So there's multiple avenues or multiple aspects to look at it. So current literature on the way they detect aimbot is basically performing some type of offline analysis on this exact trajectory pattern. Is it following human-like pattern, or is it following very snap? But typically aimbots these days, they know that this is the type of mitigation techniques that's happening, so almost none of them have this point-to-point snap, because that's what the mitigation techniques are looking for. So even these ones, they will try to do some kind of either a smooth transition or even sometimes having some kind of offset. So even if the opponent is here, they will move directly on purpose here and then move it back here to have some kind of human-like approach to it. And then there's different types of aimbots where they kind of gradually learn from the human as well. So they start off with very bad precision, but then they kind of mimic the way this user profile is to become basically like them. So different ways to use this.
You show that the patch are quite colorful, quite really easy to distinguish. Do you think maybe the player is going to try to act against it and try to find mitigations to avoid this kind of patch because they have like a certain size and things that could be easily to identify? Did you try to find maybe stealthier patch that you could integrate to the pictures as well?
So yeah, there's two things. Obviously, the more smaller they are, the more stealthier they are. So we started off with trying with just the smallest size, 1x1, 5x5, but it just didn't work. It was not able to trigger the model at all. Even the 5x5, the highest it could trigger was with a confidence of 40% or 50%, and the minimum size that we did see was for 10x10. And obviously, you're right. Right now, it's just different colors. But that's what the future work is. What I talked about is we should have better initialization of the patch based on certain map scenes. For example, if the map contains, mountains with a brown color, so the patches should, be more brown pixels with some pixels that also trigger the model. So that way they remain stealthy at that location. And again, they're only rendered for, 0.1 seconds. And the more we can reduce this, and the more we can have more integrated within the map, the more stealthier they can become.
Okay, thanks.
An additional question with this. You explained that it is displayed on screen for about 0.1 second. Isn't it easy for an aimbot to filter out this kind by image correlation, for example, to filter out that there is a patch that has been displayed for only half a second or less, and simply ignore it?
So you're saying ignore a patch?
Yeah, because they don't know yet it will exist, but in the future it will. And one of the mitigation systems that they might put in place is simply avoid images that are displayed less than half a second, for example.
So so that's why we have 100 patches. So even if they can filter for 1 patch or 2 patch or 3 patches, let's say that they see this, okay, now they have it, but then we have a distribution of patches with different properties and different features, so that even if they filter their model for specific patches, we have these. That's the reason we have multiple patches of different sizes. We can talk more about this offline. Maybe I didn't understand you
They'll do
right.
coffee break just after.
Okay.
There is still one question over there.
Hello, thanks for your talk. Recently, I see people from the Counter-Strike 2 community to make graffiti during their match to trigger aimbot, visual aimbot. My question is, I understand you show your pattern on the screen to trigger the aimbot. But there is some technology like frame generation, who are now publicly available. Does it will not counter your appearance of frame on the screen?
I'm not sure I understand it correctly. So you say there's something available that
Like
counters our approach?
Frame generation for graphic card to multi-frame generation.
So I don't know the mechanism behind it. So how does it work that it would prevent our approach from working properly?
It's like the AI it will predict the frame will come between two frames.
So okay, so you're saying that the AI will be able to predict the next frame and then be able to distinguish between the patch and the player?
Not really. We will talk that after.
Okay, all right.
Okay, we're a little late, so we are going to stop here. Thanks a lot again. So we have a coffee
Thank you.
break.